All right, good morning, everybody. So I'm going to go through a quick, hopefully 15 or 20-minute pre-lecture before we do the materials today in your group work. I got to kind of stay close to the computer because it turns out I forgot my microphone again. So hopefully it'll pick up the sound just fine. So last time we talked about the Wittig reaction, and what does the Wittig reaction ultimately do for us? It makes carbon-carbon double bonds from, so aldehydes and ketones can be converted into carbon-carbon double bonds or alkenes pretty easily using the Wittig reaction. And so we talked about this idea of using the Wittig reagent. Notice there's a phosphorus with a positive charge, a carbon with a negative charge, and pretty much so you're just going to replace the carbon-oxygen double bond with a carbon-carbon double bond. So the carbon and everything else that's associated on that carbon of the Wittig reagent becomes part of the alkene. Pretty straightforward, right? And triphenylphosphine oxide is the byproduct that we get that drives the reaction actually to the right because the phosphorus-oxygen bond is so strong. So, Wittig reagents are also known as ylides, Y-L-I-D-E. And an ylide is a molecule that has opposite charges on adjacent atoms. Okay, that's what you need to know. Okay, it's kind of like a zwitterion, but zwitterions can actually have different charges located just about anywhere. But ylides have to have opposite charges on adjacent atoms. So in this case, the phosphorus is positively charged. It has a formal positive charge. The carbanion has a formal negative charge. And so we know that carbons with negative charges, right, can function as nucleophiles, and that's how this process works. Okay, and we'll talk a little bit about that in just a moment. Now, there are two ways in which I can draw an ylide. I can draw an ylide like this, okay, which nothing wrong with that, or I can draw an ylide like this, and we actually call this the ylene form. Why am I not breaking any rules in doing that? I am moving electrons, but I'm putting 10 electrons around phosphorus. Why? Why am I don't like that term, right? Okay. But you're on the right track. Phosphorus is not in the second period. It can have more than 8 electrons around it, right? Expanded octet, right? And so we're not breaking any rules in doing so. There's still just an octet of electrons around carbon. And phosphorus can take up to 10 electrons, no problem. Okay? You will quite frequently see me put this on exams, not in this form, but in this form because it's a heck of a lot easier in ChemDraw to do it. Carbon, double bond, done. Right here I have to put the lines in, I have to put the lone pairs in, then I have to go in and put the charges. I'm not going to do that. Okay? I want to do this. But you need to know that this and this are essentially just resonance structures of one another, and you can think of them as equivalent. Okay? So anytime you see a phosphorus double bond carbon, think of an ylide. Okay? Now, how do we make these molecules, these so-called ylides? It turns out that you can buy them, many of them, but they're extremely easy to make. They are so easy to make that each and every one of you in this classroom right now could go and make an ylide, no problem. You have to have no special training or technique ability. You don't have to have really good hands in the laboratory. You can't mess this up, okay? You really can't. So the first thing that we do is an SN2 reaction on a molecule called triphenylphosphine. Phosphorus has a lone pair of electrons on it. Therefore, it's a nucleophile. And we simply react this with some type of alkyl halide. Okay? You can use secondary, but typically it's a primary alkyl halide. Typically it's an alkyl chloride, an alkyl bromide, or an alkyl iodide. It doesn't matter. It just can't be an alkyl fluoride. An SN2 reaction occurs and we get what we call a phosphonium salt. Some people actually call these Wittig salts, although that's just common terminology. That's not official. Okay? Is that an ylide? Not yet. It only has a positive charge on phosphorus. The adjacent atom has no charge, and the counterion comes from the leaving group. Right? So it is just a salt. And again, I say that you all can make these without any problem. You literally take triphenylphosphine, you put it in hexane, just a hydrocarbon. You drip in the alkyl halide of choice, a stir bar, and you stir it. And as the reaction progresses, what do you think happens? It does. Salts are not typically soluble in hexane, right? And so it typically falls out of solution. It's the easiest thing in the world to do. You see this white snowflakey stuff just falling out of solution. You filter it. You maybe wash it with a little bit of hexane to make sure it's got any leftover phosphine or alkyl halide off of it. You dry it and you're done. Yields 90% and above all the time. Works really, really well. Okay? But it's not a phosphonium salt yet, or it's not an ylide yet. It's a phosphonium salt. How do I convert that into an ylide? What do I have to do? Okay, I have to take one of the hydrogens off of the adjacent carbon atoms, or, right there, right? But would I use an acid or a base to do that?
Well, the X minus takes the H and that'll make that.
All right, so I need some type of base that's going to remove that proton, right? So you're on the right track. It turns out that it's not going to be X minus because I generate a strong acid, and strong acids can actually protonate ylides. I need a different kind of base. I need a stronger base. And so typically you will take this, you'll take a strong base, and you'll generate the ylide. Typically, this is done using really strong bases like butyl lithium. Okay? Which is why we typically don't have undergraduate students making these ylides like this, because butyl lithium is what? Why is it dangerous? We've talked about it before. It's pyrophoric, right? What's that mean? It spontaneously bursts into flames in air.
Did someone die at Berkeley?
Somebody did die. I can't remember if it was Berkeley or one of the other California schools, but yes, they did, using a lithium reagent. And so they're kind of dangerous. They're useful, but they are kind of dangerous, and you can generate the ylide. Now, there are ylides that you can actually generate depending on what R is. Okay, if R is some kind of electron withdrawing group, that makes this hydrogen even more acidic, and you can get away with weaker bases. I've actually worked with ylides, or made ylides in the past, that hydroxide is a strong enough base to generate the ylide. Okay, and we would have students, do something like that, but not working with the butyl lithiums or anything like that. We wouldn't have you all do that at this stage. So let's do a quick little concepts test. How can I convert this into this molecule? How do we need to think about this problem?
We're making a carbon-carbon bond.
What kind of carbon-carbon bond are we making? We're making a carbon-carbon double bond, right? So we know that we can do that really well with the Wittig reaction. We need to think about this backwards, right? We need to think about the product and work our way back to the starting material. And so if you start off where do I need to be thinking?
Benzene and double bond.
In this region? Right. So if I think about, that's the bond I need to make, right? And I know from the Wittig reaction I would need what? What two components do I need to do Wittig?
You need the phenol phosphorus.
Okay, that's to make the Wittig reagent. And that's right, you're not wrong. Okay, so I need the Wittig reagent.
So you need a Wittig reagent with a benzene ring.
Just a benzene ring?
One benzene ring and a carbon.
Okay. What's the other component to a Wittig reaction? So we've got the Wittig reagent, you got that down. I need what else?
Ketone or aldehyde.
I need a ketone or an aldehyde. What do I need here? So this is the bond we're talking about. Right? So I've got a hydrogen here, and I've got a hydrogen here. Do I need an aldehyde or a ketone? I'm going to need an aldehyde, right? This part is going to be benzaldehyde. And this part is going to be my Wittig reagent. Do I have that? Look up there. Do I have that? Can I make that from my starting material? You bet. I can take this and make that from the alpha bromo ethyl acetate plus triphenylphosphine, and of course deprotonated, right? So what are we going to do? We're going to take triphenylphosphine. We're going to take the starting material. We're going to form the Wittig salt. Then we're going to deprotonate that and make the illet. And this is one, because this is an electron withdrawing group, you could actually, I would have you all work on this one, because you can actually take this Wittig salt that you get, add sodium hydroxide, and you will make the illet. It's very, very easy to do. It doesn't require a strong base, because these protons are pretty acidic. Then once you have the Wittig reagent, you simply mix it with the aldehyde, and you will get the material. What kind of alkene did we just generate? It's trans. Okay? It turns out that the Wittig reaction is very bad at giving cis or trans. It gives a mixture, unless you have a stabilizing group on the illet, like a carbonyl. Okay? Illets typically don't react with esters, but that is a carbonyl, and that stabilizes the negative charge on the adjacent carbon, and it will almost guarantee that you get 100% trans configuration. If you do not have some, let's just say we had an alkyl group out here, you would have a mixture of cis and trans. Okay? The Wittig reaction is actually pretty poor at controlling stereochemistry around carbon-carbon double bonds. And so I told you all that I did a lot of research using Wittig reactions in my my postdoctoral work, and it turns out that that double bond geometry was not important for us. We were going to reduce that anyway to a single bond, so it didn't matter. So we were able to get away with it. But if you want double bonds, you have to pay attention to the stereochemistry, right? So here's the mechanism of the Wittig reaction. Again, you want to think about it, even if I draw it as the ylene form, always remember that the carbon atom on the illet is negatively charged. It's going to attack the carbon of the carbonyl, break the weak pi bond. You end up with what's called a butane. You have a negatively charged oxygen and a positively charged phosphorus. Phosphorus can obviously have more than 8 electrons, and so the oxygen attacks the phosphorus, and you go to what's called an oxophosphatine, or phosphatane, excuse me. It's a mouthful, right? It's this 4-membered ring. What do we know about 4-membered rings? They're kind of unstable. They're strained, right? And so what happens is it undergoes an elimination to form triphenylphosphine oxide plus the carbon-carbon double bond. They have observed all of these species by NMR. We know that this is how this reaction proceeds. And the reaction proceeds because the phosphorus-oxygen double bond is so strong. That's why all of these are drawn as just going in one direction, not as equilibrium. Okay? The mechanism's pretty straightforward. Okay? You know that wherever you have that carbon-oxygen double bond, that's where you're going to have the carbon-carbon double bond in the end. Right? But it goes to these two intermediates, the butane and the oxophosphatane. Okay? And so here's some more examples. So if you look at this simple aldehyde, and if you look at this illet, again, we've got a hydrogen on this carbon and just an alkyl group. What you'll see is that you get almost a 1-to-1 mixture of stereoisomers, right? So if you want to make one stereoisomer, the Wittig reaction is really not a very good reaction to do this. And in fact, you could probably find 1,000 pages in the literature on other modifications of the Wittig reaction that will help you either get the cis or the trans. And it's kind of like cookbook magic, where people have tried adding different things to the reaction to see if they can force it to go one way or the other. And so, but basically what I want you to take away is that you're going to get a mixture of stereoisomers for the most part. The Wittig reaction has also been used to make the orange pigment found in carrots called beta carotene. And so you can see that you have an ylide here, we have an aldehyde here, mix the two together. This red bond is now created, and now we have the entire extremely highly conjugated system that's called beta carotene. And all of this conjugation is why beta carotene is orange, right? I mean, carrots are carrot colored because of beta carotene, and they are that color because of all this conjugation in their double bonds. But it is nothing more than a pure hydrocarbon, but it's highly unsaturated. It absorbs visible light, and what it doesn't absorb is orange, and so that's why it appears to be orange when we look at it, right? What's beta carotene useful for? What health benefit do we get from eating our carrots? Our eyesight, right? It helps keep healthy eyes, right? And so very useful. So I'm going to skip through that. We've already talked about that the other day. We can also add amines to carbonyl compounds. So remember, just a quick review, we can have primary amines, secondary amines, or tertiary amines. And the amines that we can actually add to aldehydes and ketones are the primary amines and the secondary amines, because you need at least one hydrogen on the nitrogen for this to work. Okay? And so if you take a ketone or an aldehyde and you react it with a primary amine, usually in the presence of mild acid, you end up getting what's called an imine. Okay, so what's actually changing here? We're changing a carbon-oxygen bond for a carbon-nitrogen double bond. And even though in the book they actually show this as being going one way, this is actually an equilibrium reaction. So how can I drive the equilibrium to the right? And by doing what? Okay, I could increase the concentration of reactants. That didn't push the equilibrium. How else could I do it? Let's say my reactants are really expensive. What product? I could maybe distill that if it's a liquid, but I could certainly distill that out, right? Or use a dehydrating agent, something like magnesium sulfate or sodium sulfate, whatever you all use in lab, and absorb the water. So if I add a lot of water to an amine, it goes back, right? If I take the water out, it goes towards the formation of the amine, okay? These amines are also known as Schiff bases. You will hear chemists talk about Schiff bases an awful lot. You just need to know that that is a imine. Okay, the mechanism is fairly straightforward. Of course, nitrogen having a lone pair of electrons is a nucleophile. The carbon of the carbonyl, of course, is an electrophile. You end up forming that tetrahedral intermediate just like we have before. Notice we have a negatively charged oxygen. Now we have a positively charged nitrogen. So I have a strong base, and this is now what's the nitrogen? The hydrogens on the nitrogen, are they acidic or not acidic? They're acidic, right? So I have a pretty strong acid, and a pretty strong base, so we get a proton transfer. We get this intermediate, which is called a carbonylamine, which then gets protonated again by the mild acid that we have in the reaction mixture. Makes a good leaving group water. That leaves, you form a protonated imine, and that generates the acid catalyst. These reactions don't require much acid, actually. When I do these reactions in my lab, I literally take my beaker, I put a little bit of acid in it, and I swirl it around, and I dump it all out and rinse the flask with water. There's going to be enough acid coated on the flask itself to promote this reaction. So I literally then just mix everything together. My imine usually is a solid in my case, and it falls out of solution, and I filter it off, and I collect it. So you don't really have to add a whole lot of acid for this reaction to work. It works very well with just traces that are even present on the surface of a glass container. Okay, and so some chemists actually call that advantageous acid. Okay, but it is catalytic. Now this has real consequences for us. Okay, you are able to see this slide because of imine chemistry. Okay, so if you look at the protein, and I'm not a biologist, so I don't know all of the details of all this, but I know the chemistry part. So opsin is a protein, right, in rhodopsin that's partially responsible for the electrical signal for you seeing photons. Okay? Now, beta carotene gets cut in half, and when it gets cut in half, you have this cis double bond at the number 11 position. And it is connected to the protein opsin by an imine bond. Carbon-nitrogen double bond right there. Your eye sees something because a photon of light hits this molecule and excites this double bond, and it makes it go from cis to trans. So an electron in that conjugated system gets promoted to a higher orbital. In doing so, you technically break the double bond character. And in doing that, what can happen? Free rotation. And then that relaxes and the electron comes back down to its ground state. And you end up with you go from a cis double bond to a trans double bond. And since you have the steric crowding, that's a favorable thing, right? And when this thing changes its shape, it tugs on the protein. It literally tugs on the protein. And that's what sends the electrical impulse to your brain. And then a bunch of magic happens that I don't understand anything about, okay? But imagine if this bond to the opsin protein was a carbon-carbon double bond. It should still do the same stinking thing, but what would happen? You would die? No. But we would see for a very short period of time, and then we'd go blind. Because a carbon-carbon double bond is essentially irreversible. But what happens here? This hydrolyzes, gives me back my primary amine, and another molecule of the aldehyde that comes from this gets attached. And it's ready then to see another photon. Because the chemistry is reversible, I can see for a really long period of time. If this had actually been occurred through stronger bonds, things that were irreversible, we would have seen a flash of light the moment we opened our eyes from birth, and then we would have probably gone blind. Okay? And that probably we would have not survived as a species.
I meant your eyes.
Oh, okay. All right. And that's an oversimplification. I'm sure my biology friends that know more about this than I do would cringe at some of the explanations I'm giving you. But it is true that this has to be a reversible bond. It's enzymatically sped up. You have enzymes in your body that help with this process, but the chemistry is the chemistry. It is the same. Okay? So, if I have a primary amine plus an aldehyde or a ketone, what am I going to get? I'm going to get an imine. A primary amine plus an aldehyde or a ketone gives me an imine. If I have a secondary amine, I do not get an imine. I get what's called an enamine. Okay? So ene for the double bond, amine, the amine attached to the double bond. It's an enamine. A secondary amine plus an aldehyde or a ketone gives me an enamine. Okay? It is not an imine. And so these types of reactions work very well as well. Again, mild acid is needed for these things to be promoted. So a ketone, secondary amine, notice I get the enamine. The secondary amine can also be cyclic, and we can get these heterocyclic enamine species. We'll talk more about these enamines later when we talk about enolate chemistry, because they also behave like enolates a little bit, and they have a special role in some modern chemistry called organocatalytic processes, where we're using organic molecules to catalyze reactions, but we're not going to get into that today. Okay? The mechanism is essentially the same. The secondary amine attacks, you go through the tetrahedral intermediate proton transfer to the carbonylamine. That's exactly the same steps as you saw in imine formation. Why is it different now, though? Why is it that I don't get an imine and I have to get an enamine? We're really close to spring break, I know. Why are we different here? What's different? We've got two substituents on the nitrogen, right? There's nothing for me to deprotonate here and get an imine. So the water takes one of the alpha protons from either the, from what was on the ketone or the aldehyde and forms a double bond. And that's how we get the enamine. That's why a secondary amine gives enamines, whereas a primary amine gives imines. We get two different products, but up until about this point, well, not exactly up until this point, the mechanism is exactly the same. You don't have to learn two different things in terms of the mechanism. It's just this last step that's different. And notice they have the steps as completely reversible. Okay? All of these steps are completely reversible. So if we want to push the reaction this way, we're going to remove the water. If we want the reaction to go back, we add a lot of water. Okay, so these things can be hydrolyzed. All right, we're going to stop there. I want to make sure you all have enough time to work with your partners on the inverted lecture material. This will be due when you get back from spring break on Monday. I will be posting some stuff to Canvas next week on the Baehr-Villiger reaction. We didn't have time to talk about that in class, but you need to read that in the chapter.